past lessons, we've talked about circles and finding the distance on the arc of a circle for a given angle. What we want to do now is cause that point on the edge of the circle to move, and that's going to create what we call linear velocity. So if we have a circle of radius r, and P moves a distance S on the circumference of the circle. So we have a point out here, and it's going to move a distance, and in the past we've called it T, but we're going to call it S on the circumference of the circle in the amount of time T. So we've moved this distance, S. We've taken a point from here and we've moved it to here, our point P, and we've moved a distance S in time T. Then the speed that that point is moving, or which we would call linear velocity, because this is moving in a line in a unit of length, would be our distance T divided by the time that it took for it to move that distance. So if we had, if our distance was 5 centimeters, and it took us 2 seconds to go from our beginning point to point P, then the velocity of that point would be moving at a rate of 5 centimeters in 2 seconds, or 2.5, if we wanted to put it as a decimal, 2.5 centimeters per second. And our answers here will be given as a unit of length over time. And so we can get then our linear velocity, or the speed that it is traveling. If we had something, and let's say that it was, we moved a distance of 12 feet, and it took us 6 seconds to move that distance, then our linear velocity, the speed with which it's traveling, would be 12 divided by 6, or 2 feet per second. And it's going to be very important in this, when you're doing this, to keep track of your units. And so this is how we would get how fast something is moving on the edge of the circle. Now, while it's moving on the edge of the circle, then this central angle is also changing. So we have two things changing here. We have the linear velocity, how fast a point on the edge is changing, and then we're going to have how fast that angle is changing. And how fast that angle is changing is called angular velocity. So if P is a point moving with uniform circular motion on a circle of radius r, and the line from the center of the circle through P sweeps out a central angle theta in amount of time P, then the angular velocity, and we're going to use the Greek letter omega to show angular velocity if P is given by the formula that omega is equal to the change in the angle, or whatever size the angle is then, divided by T. So again, if you can think of it as this line moving. So as the whole line moves and sweeps out a central angle of theta in a specific amount of time, then how fast that angle is changing is equal to whatever your angle is divided by how long it took it to change from that amount. So if we had a problem and we were given that our central angle was 3 pi over 4 radians. And I didn't stress it. It said it in the formula up here, but I didn't stress that theta has to be measured in radians. So we have a central angle. Our theta is 3 pi over 4 radians. And it took it 3 seconds to travel that distance, that angular measure. And so if we want to know our angular velocity, how fast the angle is changing, it would be 3 pi over 4 divided by 3. And remember that when we're dividing with fractions, we multiply by the reciprocal of the divisor. So it would be time, we multiply by the reciprocal of the divisor. So in this case, our 3's, this is supposed to be a 3. I was getting ahead of myself in thinking. It's the reciprocal of the divisor, so 1/3. Our 3's cancel, and we end up with pi over 4, and this would be radians per second, is how fast your central angle is changing. And so we can find our linear velocity, which is how fast something on the edge is changing, how fast it's moving, and we can find our angular velocity, which really deals with how fast our point is turning. We're turning for the center. Now let's look at some applications of this. We have a bicycle wheel of radius 12 inches, and it turns with an angular velocity of 3 radians per second. We want to find the distance that we've traveled in 1 minute. Now, if you think about your circle as a point on the edge of our circle turns, or as our circle turns, if we were having a point, then however far we've gone around the circle would be the same distance that we've traveled on the ground. So you could just think if you could cut that, and then as you turned it was laid out, then that would be the distance on the ground you've covered. So if we can find out how far we've gone around the circle, a point's gone around the circle, then that will also be our same linear distance. So we want to find our distance. Well, if we think about this, we're going to have to do several things. We know that to find the distance is equal to our radius times our central angle. Well, we weren't given our central angle, we were given how fast our central angle was changing. So we need to go back and figure out what our angle was, what theta was. Well, we know that angular velocity is your angle divided by time. Well, we were given that our angular velocity was 3 radians per second. So our angular velocity was 3 radians per second. So our time is in 1 second. It was 3 radians per time. And I think I want to go back and write this a different way. It's going to turn out to be the same thing, but we're trying to find theta. So a good idea is to always start by solving your equation before what you're looking for. So if we multiplied both sides by t, we would get that our angular velocity times time would be our central angle, or our theta. Now our angular velocity here was the 3 radians per second. Then we want to multiply that by the amount of time. And our time in this case was 1 minute. Well, now we can't use two different units of measure. So 60 seconds is equal to 1 minute. So let's go ahead and change, as we multiply it by our time, we're going to change that to minutes. And so then we can do our multiplication. Our uh, seconds are going to cancel, and we would get that our central angle then was 3 radians. And we weren't needing to actually put the 1 minute. I'm sorry, we didn't need to do that conversion there. We were multiplying it by 1 minute, and we changed that 1 minute to 60 seconds. And so our angular velocity times the time of 60 seconds gives us then 180 radians. So now we know what our central angle was. It was 180 radians. We know the radius, so the distance that we're going to travel will be 12 inches times the 180, which turns out to be 12 times the 180. We could get our calculator out there. 2,160 inches is how far we've traveled then in that 1 minute. And if you needed to see what that was in feet, we could do a conversion here of changing our feet to inches. We know that we have inches, so if we wanted feet, then we would need to multiply it so that our inches cancel, and we're left with feet, and we know that there's 12 inches in a foot. So we could divide that by 12 and come up with 180 feet. And just depending upon what you were asked, this problem doesn't tell us how we want our answer, but that gives us then a way of knowing. So we've got our distance traveled. And we're going to use these formulas in several different ways as we go through here. Now, one of the things before we move on to the next problem that I want to point out here is that some of these problems, it's not, we have to find some things before we can really answer the question. And what you often want to do is start off with the formula for what you're trying to find. We were trying to find the distance, which dealt with how far we had traveled or how far a point on the edge had turned. And so we started off with that formula. We looked at what we were given. We were given the radius, but we were not given the central angle. So then we went to another formula of what we had been given so that we could find the unknown. Now we have a lot of different things that we'll be looking for. Here we're trying to find the linear velocity of a point that's moving with uniform circular motion if the point covers a distance s in an amount of time t. Okay, so we'll look at our formula. We're wanting linear velocity. Our formula for linear velocity is v is equal to the distance traveled divided by the amount of time it took to travel that distance. So in this problem then we have 10 feet in 2 minutes. So we're traveling at a rate of 5 feet per minute. And in some problems we'll actually have to do some changing of units, but in this one it's just a straightforward problem. Let's look at another one. We want to find the distance traveled. So we're wanting to find s, the distance traveled by a point moving with a linear velocity v for a time t. Well, let's start back with our formula that v is equal to s divided by t. Start with your basic formula. We're trying to find s. So we'll multiply both sides by t. So your linear velocity times time equals s, or your distance. Now this may sound pretty familiar. You probably learned back in grade school, rate times time equals distance. Well, v is our rate, our velocity, times time will equal the distance traveled. So we have 10 feet per second times our time of 4 seconds. So our seconds cancel, and we're going to end up with 40 feet, which is a unit of length. We were trying to find that. If we were wanting to find the distance, and in this case we're given our velocity and our time, and we know that linear velocity is equal to the distance traveled divided by time. So if we want s, the distance traveled, so velocity times time equals distance. Now here we've got our velocity of 63 miles per hour. But our time is 10 seconds. So what we're going to have to do is put another conversion in here of changing our hour to seconds. So we're going to just do that off to the side here. We're going to put it within the problem, but we're going to do our conversion in 1 hour. Ooh, I may not know how many seconds in an hour. I really do, but let's just go with, we know that in 1 hour there are 60 minutes. And in 1 minute there are 60 seconds. And so this is using that dimensional analysis to help us change our units. So if you notice, we're going to cancel our hours, we're going to cancel our seconds and our minutes, and we're going to be left with a unit of length, which is what we want. So this is actually a 60. So we're going to have 63 times 10 divided by 60 times 60, which is 3,600. So if we want to pull up our calculator so that we can do this, we had 63 times 10 divided by, now if you're going to do the multiplication in the denominator, remember you'll have to put parentheses, but 60 times 60 is 3,600. So that would be 0.175 miles is how far we have traveled. So we had to do some dimensional analysis there to be able to come up with that value, our distance that we had traveled. Okay, let's look at another one. Here we've got that point P sweeps out a central angle theta as it rotates on a circle of radius r. Find the angular velocity of point P. So we're wanting to know how fast the angle is changing. So we have a central angle theta. Now if we remember, that's our omega. If we start with our formula, that omega, angular velocity, is equal to your central angle divided by time. It's always your distance divided by time. So if we want our angular velocity, it's going to be 3 pi over 4 divided by 5 seconds. And to divide by the 5, we're going to multiply by 1/5. And that ends up being 3 pi over 20, and that would be radians per second, would be our angular velocity. So we've got some nice little formulas then that we're going to use as we go through and find a lot of different things. We have several applications here, and where we're going to be able to use these. Now this problem is to first of all understand it a little bit, it's a little different, but it's a neat problem. There's a lighthouse that is 100 feet from a long straight wall on the beach. The light in the lighthouse rotates through one complete rotation once every 4 seconds. Find an equation that expresses L, the length of the light, in terms of time t, where L, or when L is, find L when t is half a second, 1 second, 1.5 seconds, which will just be a matter of substituting in. So to picture what we have here, we have us a wall, and then out in the ocean somewhere, we have us a lighthouse, or off the beach. We have us a lighthouse. Now, there's a light and it rotates, and as it rotates, you know, if it's shining here, we'll just put it as it starts shining. Let's make that a dotted line so you can think if it were shining straight, it would be here, and that would be the length of the light. But as it starts to rotate, it moves down the beach, and as it does, the length of the light, okay, if this is the length of the light, it's here, and then as it moves down the beach, that length is going to be changing. And we can know that eventually it's going to travel all the way around where it's shining. Now, it usually shines out both sides, so it again would be starting there, and it would come around and be shining over here, and then we're going to be going back again. So we're wanting to know what the length of this light is after specific amounts of time. And so we're going to call this L. Now we know that the distance at this point was 100 because it told us in the problem it was 100 feet from the beach. So we can see our angle's changing, and if we don't need it for this problem, but we could also find out, well, how far down the wall is the light shining? So there's a lot of different things that we could be finding here, but we need to find L. So first of all, we know that this is the angle that's changing. So we're going to call this our theta. And we need to find L in terms of theta. And as we want to solve for L, and there's different ones that we could use, but because we want to use the 100 in this, and we want our L to be easier to find in the numerator, we could use the cosine, but the cosine of theta is the adjacent over the hypotenuse, and that would make that a little bit more difficult. So let's use the secant of theta. This is one of the few times that we're going to use secant. So the secant of theta is equal to the hypotenuse over 100, or then if we multiplied 100 times the secant of theta equals L. So we've come up now with a formula for finding L. And it's 100 times the secant of theta. If you were wanting to find the distance, as I said, you could do that over there. Well, we would be talking about opposite and adjacent, so you would be using tangent. So you've got to look at which one you want to find. We're wanting to find L. So we use secant. Well, that's real good, except we now need something for finding theta. Theta's changing because this light is rotating around. So theta is changing. So let's see what we know about theta. We know that our angular velocity, it said that it rotated, it made a complete rotation, which would be 2 pi radians in 4 seconds. So our angular velocity then would be pi over 2 radians per second. And that we got from where it makes a complete rotation every 4 seconds. So that's our angular velocity, but we want theta. So let's go back and think about our formula. Angular velocity is equal to our central angle divided by time. So if we take our angular velocity times time, that gives us our central angle. Okay, we've got our angular velocity is pi over 2 times time would be theta. And time's going to change, so we can't put that in just yet. So now we can write this as 100 times the secant of pi over 2 times t equals L. And we've come up now with a formula for finding the length of this line at any point in time. So let's go through and then and see what we want to deal with. If we, if we wanted it at time 0, we know at time 0 it would be 100 feet because it would be shining straight out. Well, at time 0, when t is 0, then this is 0, and the secant of 0 is 1. Remember, the secant's the reciprocal of cosine. Cosine of 0 is 1, so the secant of 0 is 1. And 100 times 1 would be 100. So we can see at the start then the length of that line, because this would be right back to here, it'd be shining straight down the wall, would be 100. Okay, we want to know it after half a second. So see if we can move this up just a little bit. Then we would plug in times the secant of pi over 2 times 1/2 second. And so we would have 100 times the secant of pi over 4. Okay, secant of pi over 4. Oh, pi over 4 is the same as 45. That's our reference angle. The cosine of 45, or pi over 4, is square root of 2 over 2. So the reciprocal then, the secant of 45, we got that by rationalizing 1 over the square root of 2 would simply be the square root of 2. So 100 times the square root of 2 would be our length. And since we're actually needing a length, let's see what that is. 100 times the square root of 2 that would be approximately 141 feet. So 141 feet. Okay, if we went to 1 second, well, then we would have 100 secant of pi over 2 times 1, which would be pi over 2. Well, that's 90. Now let's think on this. The cosine of 90 is 0, so the secant of 90 is undefined. Now, what's it trying to tell us here if it's undefined? We can't multiply 100 by undefined. We can't put 100 times undefined. That doesn't really make a lot of sense. So let's think of what's happening. If it's pi over 2, then if we went up here, that means we've rotated out this way. We're shining straight out, and so the length of that line, can you actually measure it? If there's nothing to block it, then you don't have an end. And so that's what it's letting us know there, and it's really kind of neat the way that that works out. And then if we want 1.5 seconds, then we would have 100 times the secant of pi over 2 times 1.5 would be 3/2. So we end up with the secant of 3 pi over 4. Well, again, our reference angle's 45. So we know again it's going to be the square root of 2, but this puts us in the second quadrant, so it's negative square root of 2, which we found out we did that up here, uh, except it was a positive, but we would end up with negative 141 feet. Now, is that making sense that we've actually ended up with a negative 141 feet? Well, let's go back to our picture. And let me see if I can uh, do this and in a different color so that we can see what's happening. Okay, we started off here. So we've rotated, whoops, okay. 45 degrees was our first one, so that would have been that distance. And then our 1 second, remember that put us straight out here, so you can see why that doesn't make sense. And then if we've rotated around 135, well, we're off in this direction. And again, that doesn't necessarily make sense, but it says it's negative because remember the light shines out in both directions. And so we're shining out in this distance, and that's why it deals with the negative. The light shines in both directions on the lighthouse. Here it makes sense that it's 100 feet, but remember at the same time, the light's shining out this way, which is going to keep on going. So it would talk about the negative, the lights to give us a distance, it would give us a negative on that one also. And so this is what we're dealing with as we look at how the length of that line is changing as we go around. And when it's one side shining in one direction, well, the other side is also shining in this direction. And so it would be the opposite of that. And so that makes that pretty neat. Okay, that's a neat problem that we have that's dealing with linear velocity and angular velocity. Okay, let's look at the next one, which isn't quite as involved or as hard as that one. It simply says that point P moves with angular velocity omega on a circle of radius r. Find the distance s traveled by the point in time t. So again, we need our distance traveled. Ooh, distance traveled. Well, we know our formula for the distance on the edge of a circle is s equals r theta. So we've got to come up then with our theta. We're given our angular velocity, we're given the radius, but we're not given theta. So we go to our other formula for angular velocity, remember, is theta divided by time. So our angular velocity times time will equal theta. Well, our angular velocity was 4 radians per second. Our time was 5 seconds. So the seconds cancel, and we end up with 20 radians. Now we can find how far something's traveled. It's going to be the radius, which was 2 inches, times 20, our central angle of 20 radians, which would be 40 inches. Remember, the radians is just saying the real numbers. We don't have to keep track of the radians within the problem, unless, we end up then with our 40 inches is how far we traveled. If we look at another one like that, it looks like we're almost given the same thing. So again, we're wanting to find S, and I always like to start out with my formulas. S is equal to r theta. And we have the radius, but we don't have theta. We have angular velocity. Angular velocity is equal to theta divided by time. So angular velocity times time equals theta. Well, our angular velocity was 10 radians per second, and our time is 2 minutes. Oh, we can't deal with seconds and minutes. So what we're going to do is change our minutes. And I'm just going to go over here and put my conversion factor in 1 minute. There are 60 seconds. And it's kind of easy to know where to put them because you're needing them to cancel. So the minutes had to go in the opposite place. The seconds had to go in the opposite place. And I keep leaving off my zero. So we have 10 times 2 are 20 times 60. So we have 1200 radians is our central angle, is theta. So now we can find the distance that we traveled on the edge. It's going to be the radius of 6 feet times 1200 radians, which gives us 7,200 feet, is how far something on the edge traveled in that amount of time. Okay, let's look at some problems where we're trying to find angular velocity. Here we want to find our angular velocity in radians per minute if we're given RPMs. Now an RPM stands for revolution per minute or rotation per minute. Every time we go around in a circle, we've gone through 2 pi radians. So each revolution is 2 pi radians. So if we need this in radians per minute, we're simply going to multiply this by 2 pi. So 10 revolutions per minute would be 20 pi radians per minute. If we wanted 33 and a third, well, if we change that to a fraction, that would be 100 thirds times 2 pi. That's how many radians we go through in one revolution, and we're going 33 and a third revolutions. So that would be 200 pi over 3 radians per minute. And a lot of times when you're talking about engines or things turning, it's in revolutions per minute instead of radians. So you're going to have to get that central angle. And you'll always then multiply your number of revolutions times 2 pi. So here we want to find our linear velocity, and we're given that we're going to do 2 inches, and our central angle, our angular velocity is 5 radians per minute. Well, we need to look then at our formula for linear velocity based upon angular velocity. And I don't believe we've gotten that formula yet. So let's look at it. Okay, let's think of our linear velocity. And we know that linear velocity is equal to our radius times our central angle. We know that. That's our distance, excuse me, not linear velocity. That's our distance. Distance is equal to the radius times the central angle. But we want velocity, and we know that linear velocity was our distance divided by time. Well, let's just divide both sides here by t. That's linear velocity right here, distance divided by time. And what we have over here is r times theta divided by time. We can break that up. We only have to divide one of them. By that, it's not a distributive property. And theta divided by time is angular velocity. So linear velocity is equal to our radius times angular velocity. And you can see that the faster the angular velocity is, then the faster the linear velocity would be. It's going to be proportional, or the longer the radius, then the faster the linear velocity would be. So that's why the children's Ferris wheels have a very small radius, where the adult ones may have a big radius and they may turn at the same rate, but you're moving much faster on the edge as you change your radius. So here's us another formula then for linear velocity. It's our radius times the angular velocity. So now let's look at that problem. We want to find our linear velocity given the angular velocity. Well, our linear velocity is equal to the radius times the angular velocity. So that would be 2 inches times 5 radians per second. Now we do have to keep track of our hours, but remember the radians doesn't come into play here. So our linear velocity would be 2 inches per second, is how fast we would be moving there. Not 2. 2 times 5 is 10, isn't it? Okay. 2 times 5 is 10. So 10 inches per second. If we look at this problem, we want to find our linear velocity, which we know is the radius times the angular velocity. Well, our radius is 1 foot, but it didn't give us our angular velocity. It gave us our rotation. Well, our angular velocity is our number of rotations times 2 pi. So here our angular velocity would be 40 pi radians per minute. We had 20 revolutions. Each revolution went through 2 pi radians. So 40 pi radians per minute. So we end up with 40 pi feet per minute. Now right here, if you were going to use this in a problem, keep it exact. But if not, it doesn't necessarily make a lot of sense to go out and measure something that's 40 pi. So if we went to our calculator, 40 times pi, that would be approximately 126 feet. But the 40 pi is an exact answer, which you can use in other problems. Okay, so we've had some problems there. Look at this one. You know, a lawnmower has a blade that extends 1 foot from its center. So that would be its radius, 1 foot or 12 inches. The tip of the blade is traveling at the speed of sound, which is 1,100 feet per second. Through how many revolutions per minute is the blade turning? Oh, so this one's kind of going backwards. We're trying to find our RPMs. Well, we're still going to start with the formula that we know, that linear velocity is equal to the radius times the angular velocity. We know the radius, it extends out 1 foot. So we have a radius of 1 foot, and we know that it is traveling, the tip of the blade is traveling at the speed of sound. Ooh, the tip of the blade. The tip of the blade is dealing with linear linear velocity. So it's our linear velocity here that's the 1,100 feet per second. And we're trying to come up then with our angular velocity. Again, a lot of times it's easier, which I didn't do here, is to go ahead and solve your equation so that it's already set up. But what we have is 1,100 feet per second divided by 1 foot. And so we're going to end up with 1,100 radians per second. Our feet canceled. So that's our angular velocity. Now, what we wanted though was how many RPMs, how many revolutions per minute. And so we know that every time we go through, oh, we didn't do one thing here, did we? I forgot. Okay. Well, we'll take care of that as we go through here. That's radians per second. We're going to want revolutions per minute. So we're going to have to do some conversions. But we're going to have, so let's go ahead and do that part. You have to be careful in all these problems because a lot of times there's more than just the first computation. It's that many per second. We're going to want revolutions per minute. And so let's find out how many radians per minute we go through. We need to get rid of seconds. And we need minutes. So we put the seconds in the place where it would cancel, and we know that there's 60 seconds in 1 minute. There's your conversion factor. So the seconds cancel, and we end up with 6,600 radians per minute. So now we've got the right units of time. But we need to get now how many revolutions. Well, we know that one revolution is 2 pi radians. So what we're going to do is take this 6,600 and divide it by 2 pi. So there goes our radians, and that will give us then revolutions per minute, RPMs. And we could do some canceling if you wanted to come up with an exact one. Both of those are divisible by 2. So an exact answer would be 3,300 over pi RPMs. And that doesn't make a lot of sense to us, so we could then divide 3,300 divided by pi. And so that's approximately 1,050 RPMs. So those things are turning very quickly. That's how many RPMs there would be as we went through. And I think I've left out something. I left out a 0. Up here, 1,100 times 60, I just multiplied it by 6. You can see I've left out a 0 here and a 0 here. So let's go back and do that division again. So 33,000 divided by pi. That would be 1,500 or 10,504. That's a lot more. So you can tell how quickly it's turning and why you have all of those precautions of keeping your hands and your feet away from the turning blade. All right, we've got one more problem that I want to look at, or a couple of more problems that I want to look at. And it's just all different types of applications that you can have as you're dealing with linear velocity and angular velocity. And a lot of times we have things that are dealing with pulley systems, or where you're using a cable to cause things to turn. But this says a cable car is driven by a large 14-foot diameter pulley called a sheave. The sheave turns at a rate of 19 RPMs. Find the speed of the cable car in miles per hour by determining the linear velocity of the cable. Now basically what happens is you've got this sheave and a cable is going around it. And however fast a point on the edge of the sheave is moving is how fast that cable's moving. And then it's connected to something else. Now often It's connected to something smaller or something bigger, which is causing things to move faster or slower. Uh, if you got into bicycle tires with gears, then you've got a chain that's causing one thing to turn. But in this case, this is just causing, this is the pulley system that's pulling the cable cars because they actually have the cable up there. So we're wanting to know then how fast this cable car is going in miles per hour, which is basically the linear velocity of the cable. So let's think of some formulas that we have. We know that linear velocity is the radius times the angular velocity. And we're wanting to know the linear velocity. Our radius is 7 foot. It's a 14-foot diameter, so the radius is 7 feet. And then the sheave is turning at a rate of 19 RPMs, which if we multiply that by 2 pi, each revolution, remember, is 2 pi radians, then that would be radians per minute. So our linear velocity turns out to be 7 times 19 times 2 pi. And if we multiplied all of that out, let's just get our calculator. So we have 7 times 19 times 2. We're going to figure up that in exact, so that would be 266 pi. And that would be feet per minute. Now that would be an exact answer, approximately, and we'll do some other changing in a minute, but let's get this one so far. So if that would be approximately, then that times pi would be approximately 836 feet per minute. But if you look at the problem, it didn't want feet per minute, it wanted miles per hour. So now we're going to need to do some conversion. So I'm going to keep the 266 pi right now, feet per minute, and let's see what we need to change. We need to change our minutes to hours. So we need minutes in the top, hours in the denominator, and we know there's 60 minutes in an hour. We need to change feet to miles, so we've got to get rid of our feet and change it to miles. And in 1 mile, there's 5,280 feet. So now we notice our minutes cancel, our feet cancel, and we're going to be left with miles per hour. So we could get an exact answer, 266 times 60. So that would be 15,960 pi miles per hour. That's an abbreviation we often use for that, miles per hour. But again, that doesn't make a lot of sense to us. So, divided by 5,280. I didn't do that, did I? Let me go back. Let me erase this first of all. Well, I didn't do the whole conversion. It's that 266 times pi times 60 divided by 5,280. So let's just go ahead and times pi. Then divided by 5,280. So that's approximately 9.5 miles per hour. We just went ahead and did the whole conversion. Miles per hour is approximately how fast that's going. I had it written here, I just didn't go through. And we could have done that, divided by that, and gotten it still an approximate answer, but we just went ahead and did the whole computation. So that gives us a way. We used our linear velocity. We knew the radius, and we knew how fast it was turning in RPMs, multiplied by 2 pi, and we can get then radians per minute. But then we did have to do our conversion. Now let's look at this one, and what we have here, it's a similar problem, but it says a cable car uses a 12-foot diameter sheave to drive the cable. To keep the cable cars moving at a linear velocity of 10 miles per hour, how fast would the sheave need to turn in RPMs? So this one's going backwards. We're setting it up. We need to go a certain speed. So how many RPMs are we going to need to do? So what we have then is we've got our sheave, and it's 6 feet in diameter. So let's go ahead, and what we need, we know that linear velocity is the radius times the angular velocity. Well, in this case, we're needing to know our angular velocity. So our linear velocity divided by the radius would be our angular velocity. Our linear velocity was 10 miles per hour. Ooh, miles per hour. Divided by r, which is our radius, and our radius was 6 feet. So dividing it by 6 feet is the same as multiplying it by the reciprocal 1 over 6 feet. And I did that because we have all these units. Ooh, we're going to have to do some conversions here because we can't divide miles by feet. So let's do our conversion. We know if we get feet divided over miles, that our feet will cancel and our miles will cancel, and 5,280 feet in 1 mile. So our miles cancel, our feet cancel, and what we're going to be left with then is radians per hour. So okay, let's look at that then, and we'll get the calculator out. Okay, make sure I'm doing this right. Now why am I doing that 60 minutes? Okay. Okay, we need to add one more thing. I'm sorry. I was thinking and looking at this. This is RPMs. So we need this in radians per minute. And we've got it in radians per hour. I said that and I was thinking there's something else I need to do here. So we need to change our hours to minutes. So our hours need to cancel. And we know that there's 60 minutes in an hour. Now let's get the calculator out. And we've got in the numerator 10 times 5,280. Then we want to divide that, and we need the parentheses for the denominator, 6 times 60, or you could have done that in your head. And so we end up with approximately 147, and I'm going to keep that answer there because we're going to do something else with it. So 147, and that's radians per minute. But we didn't want it in radians per minute. We wanted it in revolutions per minute. Well, we know that each revolution is 2 pi. So we're going to take this and divide that answer by 2 pi. So we get approximately 23.3 RPMs. So that's how fast you've got to set it so that it will keep the cable car going at a speed of 10 miles per hour. Okay, so these are different ways that we can use our formulas for linear velocity, which was the distance divided by time, and the angular velocity, which was your central angle divided by time. And then we also gave a second formula for our linear velocity in terms of your angular velocity. So it was your radius times your angular velocity. And then the other thing that we looked at was that one rotation was 2 pi radians. And so if you were given in revolutions per minute, then you had to change that to radians per minute. And so it would be 2 pi radians. And dealing with this, we can look at how things change, how the angle changes, and then how fast points on the edge move. But always begin with a formula and then substitute in what you know. If there's something then that you don't have, look at your formulas to see how you can solve for that.